All right, good morning, everyone. We're going to get started with our third and last session on ML and AI. We have, again, the usual 6 papers that we've been doing throughout the week. Getting us started today will be Hamza, who is from the University of Southern Carolina, and he's going to, did I say California? It's in the States. We're close-ish. Sorry about that. And he's going to talk to us about some various constructions that are very useful for some privacy-preserving machine learning.
Hi everyone, I am Hamza Slim from University of Southern California, and today I'll be talking about different techniques for training privacy-preserving machine learning models using secure lookup table computation. This work was done along with my co-authors Amir Zia Shahabi, Professor Naveed, and Professor Salman. So let's get started. So starting off with some background, we know that if we have large data sets collected from diverse sources, we are able to train better machine learning models that are able to generalize better. However, there are certain challenges associated with collecting large amounts of data, such as privacy concerns, laws and regulations, and there could be also competition between different businesses that may not want to share their data with each other. So the solution to this problem is privacy-preserving machine learning that allows us to train machine learning models without having to disclose the private data to any entity. So in this work, we'll be dealing with secure multi-party computation, in particular with two-party computation that can be used to train machine learning models. So let's quickly look at our setting. So we have a number of different clients. Each will have their own data sets, and they want to train a joint machine learning model on their data set. However, they do not want to share this private data with each other. So what they can do is they can allocate two servers. They can create secret shares of their data and send the secret shares to the servers. Note that these secret shares do not leak any information about the plain text data set. Next, the servers can communicate with each other and run secure computation protocols. And as a result of that, they are able to train the machine learning model. The model is secret shared between the two servers and does not leak any information about the actual plain text model. Next, they can combine these secret shared models and get the actual model, which can be sent to the clients. So this is the overview of how two-party computation works for training machine learning models. So what are the bottlenecks in current privacy-preserving machine learning approaches that we have? Here are some of the prominent works that present 2PC, 3PC, and 4PC works, but they suffer from two common problems. The first one is that they use inefficient protocols to compute nonlinear activation functions during training. And the second problem is that often they use some non-standard or approximate functions because computing the actual functions could be hard, which results in accuracy loss. So our contribution in this work is we present a new protocol, new lookup table-based protocols that can be used to compute arbitrary functions in secure computation. In particular, we present two protocols, Hawk single and Hawk multi. This allows us to replace the nonlinear activation function computation during training with table lookups. Apart from that, we also initiate the study of a relaxed security model for privacy-preserving machine learning. So in this work, we present both leakage-free methods, and we also present methods that have some excess pattern leakage, but they allow us to significantly reduce the computational resources that are required while training. Apart from that, we also implement our approach and compare it with past works. So our results show that the training time can be reduced up to 688 times compared to the state-of-the-art two-party computation protocols. And we are able to do this while preserving plain text training accuracy. So looking at machine learning in this work, we'll be dealing with logistic regression and neural networks. So one important thing to note in these two algorithms is that there are just three main type of operations that we need to consider while training these models. The first one is addition operations, then we have multiplications, and then we have computing nonlinear activation functions. So addition and multiplications can be done by using simple protocols for multi-party computation. But for activation function computation, we'll be using table lookups while training. So let's look at how our Hawk lookup table protocols work. So we have two parties, party A and party B, and each will be given a lookup table as a result of the offline pre-processing phase. Each lookup table has key value pairs. If you look at the keys, they are a pseudo-random function of the input x and some random key, and the value is just a secret share of the output f of x. So let's see how a single use lookup table work. We have the two parties. Each will have their secret share of some input xj that they want to perform lookup on. And then each of the party will have some random keys that will be generated in the offline phase. And then each party will be given a lookup table. If you look at the lookup table of party A, the key is of the form hash of x1 plus hash of k1 appended with C. C here is the index of the lookup table. Now let's go through the steps how lookups will be performed in the online phase. First of all, party B will send his share of xj masked with hash of k1 appended with C to party A. Party A will add his share of xj in this value and eventually compute this term, which can be used as a key in the lookup table. So it will query the table with this key and get the share of the output. Similarly, party A can send his share of xj masked with this hash, and party B can add his share of xj in this value, get the key, and use this key to query his table and get the output of yj. So this is the overview of how our single-use lookup tables work. So what are the pros of using this protocol? One pro is that it's a simple protocol which just requires one round, and the security is based on one-time pads. And it is also quite efficient. So for one function evaluation, we only require 0.2 milliseconds. But there are some cons to this protocol. First one is that these are single-use tables, so we cannot reuse a table multiple times. So for example, if while training we have to compute a sigmoid function 100 times, we'll need to have 100 such lookup tables generated during the offline phase. So this adds a overhead to the offline phase due to the computation and storage cost of these lookup tables. But still we argue that this protocol is useful for training logistic regression or for secure inference. However, this is not very practical for training neural networks, where we might need to perform a lot of functional evaluations. So for that, we present our multi-use lookup table protocol. Before going into multi-use lookup table protocol, let's discuss metric differential privacy. So metric differential privacy is just a natural generalization of the normal differential privacy that most of us are aware of. And it allows us to model situations where indistinguishability is expressed as a metric between secret inputs. So one motivating example we provide for metric differential privacy is the geo indistinguishability example. So suppose we have a user who wants to know the locations of restaurants near him. So instead of sending his actual location to the server, he can share a noised location. So he can get some noise using metric differential privacy, add that to his location, and share this obscured location to the server, and the server is able to provide the user with some restaurant recommendations without knowing the actual precise location of the user. So this is the concept we'll be using in our multi-use lookup table to hide access patterns. So let's see first how multi-use lookup table work. So again, we have the two parties. They have their shares of the input xj, and also they have some keys k and s. These are generated in the offline phase, and they have their tables, lookup tables. So if you look at the keys in the lookup tables, they have this term g. G here is the generator of an elliptic curve, and the security of this multi-use lookup table depends on elliptic curve discrete logarithm problem, which just means that if we have some random s0 and we compute, for example, s0g, looking at this value, the adversary is not able to get any information about s0. So let's see how this protocol works. First of all, we have to run a share convert protocol. So this is a very efficient protocol. It just requires one round of communication. And as a result of this protocol, the parties are able to get shares of capital S xj. After that, party B will send this term to party A. Party A will multiply it with his key k0. Similarly, party A can send this term to party B, which party B can multiply with his key k1. After that, they can exchange these two terms with each other, and after adding these two terms, they can get the key to the lookup table. Using this key, they can get the shares of the output. So this is the overview of how multi-use lookup tables work. What are the issues with this current protocol? The problem is that the lookup keys here are deterministic. We cannot, so this leaks some information about the access patterns. So the solution is to employ matrix differential privacy and add some noise to the lookups to hide the access patterns. So again, the lookup table works. The lookup table protocol works in a similar fashion, but in addition, we had some random noise to the input to hide the access patterns. Looking at the results, let's see how our logistic regression compares with the existing work. So in this table, we are comparing our protocols with secure ML, and we can see that in both LAN and WAN settings, our protocols are much more efficient for training on MNIST dataset. Similarly, if we look at the offline phase for multi-lookup table is more efficient because we are generating less lookup tables. If we look at the accuracy comparison, we can see that our protocols are able to achieve accuracy very similar to TensorFlow's plaintext model in various settings and on various data sets. If we look at the neural network training, again, we see a similar trend. In this table, I'm comparing our protocols with a number of different two-party and even three-party computation protocols. And in both LAN and WAN settings, we can see that for example, for the offline phase, our tables are able to complete it in less than half an hour for a 3-layered neural network. Other protocols require several hours. Similarly, for the online phase, our Hawk single protocol just requires 1 minute, and Hawk multi protocol just requires 6 to 7 minutes for training on a 3-layered MLP, whereas other protocols may require several hours. Similar trend is seen in the WAN settings, where our protocols are much more efficient than the existing state-of-the-art. If we look at the neural network accuracy numbers, so we can see that on MNIST dataset with a 3-layered network, we are able to achieve accuracy very similar to plain text training. So in conclusion, we present two novel lookup table protocols that can be used to compute activation functions for PPML. And we can do this while achieving plain text training accuracy. And beyond activation functions, we argue that our protocols can be used in various multi-party computation applications. Thank you so much.
Sorry. All right, we have time for a question. Okay. So just as something that I think you maybe just didn't have time to go into, I was wondering if you could make it a bit more explicit within this context what the different parties can and cannot learn given they know this protocol is being used.
Yeah, so basically we have two protocols. One is the Hawk single protocol, which is a leakage-free method. So the parties do not learn any information about the inputs if they use this protocol, but it requires more computational sources. And then we have this Hawk multi protocol. In this protocol, the parties do not learn the input values themselves, but they learn some frequency or access pattern information when some values are repeated. So to limit the leakage, we use differential privacy.
Okay, I'll follow up with you later. I think this might require a longer conversation. We have time for one quick question, or we can move on to the next speaker.
A short question. How big is your lookup table that can be practical use?
Yeah, that's a good question. We have a number of different activation functions, and for each activation function, we need a different size lookup table. So we explained that in detail in our paper, but for functions that such, for example, ReLU and DReLU, which are very common and comprise most of the activations during neural network training, we are able to reduce the size of the lookup table to just 32 entries. And for other lookup tables, they such as sigmoid, they might be larger tables, such as for sigmoid, we use a table of 2 raised to power 16. So the input we consider are 16-bit inputs. So it depends on the lookup table.
All right, let's thank the speaker.